All right, so I'm going to start with just a brief outline of what I'm going to be talking about today. So the first will be a little bit of background on MRI, functional MRI, and the MRI ontology. Touch briefly on some of these statistical ontologies that we used as imports or as motivation for this, and then finally I'll talk about sort of what got us into looking at fMRI in the first place. The bulk of the talk will be on the new fMRI classes that we added to MRIO. So these will be things like coverage of how fMRI data is acquired, how we can map brain activity in the brain and represent that in an ontology, and how we can represent the statistical inference of data from fMRI and how that kind of works with the rest of biomedical imaging as a whole. And then I'll touch briefly on some of the statistical ontologies that I have reused here and a couple of the challenges that we encountered in borrowing from multiple ontologies. And then, of course, a brief conclusion slide. So to begin, MRI or magnetic resonance imaging is a technique used to measure the physical structure of a tissue in three-dimensional space. In contrast, functional MRI or fMRI is used to look more at the activity over time, and so you end up with these four-dimensional data sets as opposed to three-dimensional. I'd like to draw your attention to the figure over here because it's a nice representation of what both 3D MRI and 4D fMRI would look like. You can see in the background the nice brain-looking thing is a 3D MRI. That is a structural MRI. The highlights that are overlaid on it are derived from 4D fMRI, and so that is a map of activation in the brain. It's just a network of activity called the default mode network. It's just what is most active when you are daydreaming. And so this is important because most public neuroimaging data sets that are available are for fMRI studies. They're on a website called openneuro.org. They've done a tremendous job of standardizing and promoting the reuse of neuroimaging data throughout neuroscience. However, interpreting fMRI data depends not just on the acquisition, but on a lot of statistical modeling that's used to link the observed signals to cognitive or behavioral variables. So it's not very straightforward to just get your four-dimensional image and get a nice activation map like you see in this figure. And so a formal representation of these concepts would be essential for reproducibility. The MRI ontology, or MRIO, is something that we have developed to capture the process of acquiring and analyzing more or less structural MRI. We had one placeholder class for fMRI that we didn't really use before, so now we are building it out here. The statistical ontologies that we reused for this work were STATO, the statistics ontology, and OBCS, and both of those build off of OB, so we borrowed some classes from OB as well. So each of these are very valuable, but they have slightly different scopes, and they don't necessarily capture the way we would do statistics with three-dimensional and four-dimensional imaging data. They provide a very strong base, so we ended up reusing some of these terms and building them out in an imaging-specific way. And so that's mostly our motivation. I won't really belabor the point too much more than we wanted to fully capture the process of working with fMRI data, since it is very readily available. There is a lot of data. There are a lot of different ways you can analyze it. There are already very good statistics ontologies in the OBO Foundry, and so we sought to reuse those and apply them to working with imaging data. So next I'm going to talk a bit more about how we extended MRIO to cover fMRI. So to begin with, MRIO was the work of a few years. It was my thesis work. It was also the thesis work of Alex Steele's previous PhD student before me. We addressed the need for a common language for MRI. And like I mentioned earlier, we focused mostly on structural MRI. So with this work, we sought to represent the process of acquiring fMRI introduce entities for derived artifacts such as brain activation maps. So if you think back to the figure I showed earlier, that's an example of a brain activation map. I'll talk a little bit more about what that really means in a couple of slides, as well as defining classes for representing how we do statistical inference on these images. To begin with, fMRI acquisition relies on a different kind of signal than you would normally use for 3D structural MRI. You would need some sort of signal measuring brain activity, and so these we all place subclasses of scalar measurement data. These are the blood oxygen level dependent signal measurement data, or BOLD signal. There's also arterial spin label and vascular space occupancy. Those are ASL and VASO respectively. These are just ways of measuring the way that blood moves throughout the brain, more or less, and how that relates to brain activity. And so these are all essential parts of acquiring an fMRI image data set related to the physiological process that we are working with. And so we were able to model the process of acquiring this and what kind of fMRI data that we get as a result of it. Following this, we are able to take these as an example here, the BOLD signal. BOLD is the one that is most commonly used, and transform that into what we call a brain activation map. We call that a data item that is a representation of brain regions that exhibit statistically significant changes in neural activity in response to an experimental task or stimuli. And so here, as an example, is the same figure as earlier. The areas that are glowing are what we call a BOLD activation map, or a blood oxygen level dependent activation map. It's just saying where metabolism in the brain is going on over the course of this scan. That's where these areas are functionally connected, or where there is organized brain activity. And so these are all the output of a process that we call functional mapping. The overall process is represented here. So we have our BOLD signal measurement data. It's part of a functional magnetic resonance imaging assay. This produces the image data set, very long labels. In the real world, we always abbreviate it. That would be a BOLD fMRI data set. That is the input to a functional mapping, and the output of that is a BOLD activation map. And so that is just a map of where organized activity within the brain, where that would be located. And so we mostly work with BOLD data. Like I said, there's also the arterial spin labeling, or ASL, and then the vascular occupancy, which is VASO. Those also have analogous classes. And so we can take that a step further. We can do statistical inference on these activation maps. So we have a general class called statistical inference applied to image data set. In the interest of time, I won't read all of these definitions, but this we'd like to think of as a very general class that can be used not just for fMRI or MRI even. It can be used for any other kind of biomedical imaging data. Things like PET. PET has a lot of statistical analyses to work with and draw inferences from PET data. So this would also apply to that. Same applies to the image data set analysis based on a general linear model, which builds off of this class we define here, or we introduce here, as general linear model time series regression. That's just using a general linear model over this set of 4-dimensional data. The general linear model is something that we have built out from Stato. I'll talk a little bit about that in a couple of slides. And then finally, there is something called a dual regression analysis of fMRI data. That is a series of 2 general linear model-based regressions used to draw inferences from your imaging data mapped to some sort of dependent variable. So as an example here, we have our activation map of the default mode network, and we use a dual regression approach to find where in the brain connections to the default mode network moderate the effect of cognitive rehabilitation therapy. This is a study that I was involved with a few years ago, but this is just an example of how we would use this in the real world. And finally, I'll wrap up with a brief overview of what we have imported from existing OpenFoundry statistical ontologies. So I mentioned earlier, Stato and OBCS were the main ontologies that we reused. From Stato, we heavily reused the regression analysis method class, as well as regression coefficient, ordinary least squares estimation, and design matrix. Those are all things that go into that general linear model, or GLM, that are used as sort of the bread and butter for doing statistical inference from imaging data. From OBCS, we relied heavily on the multiple linear regression analysis class, as well as the independent component analysis dimensionality reduction. There's a lot of different ICA type analyses that you can do with fMRI and PET data, so this was a very useful term for that. And so through this reuse, MRI avoids redundancy while grounding domain-specific extensions in broadly accepted statistical definitions. I mentioned at the beginning there was a little bit of a challenge in reusing statistical terms from a couple of different ontologies that have slightly different scopes. Both, as you can see on this previous slide, both have regression-related classes, but they make a couple of different assumptions at a couple different levels of abstraction. There's also a difference in scope. Stato is a very it's a very basic math kind of ontology. OBCS seems a bit more applied toward actually doing clinical statistics, so there's a little bit of an overlap. Stato provided a very nice foundation to build on for general classes. OBCS seems a little more geared towards making classes for practical analysis. So there is a bit of a tightrope to walk when choosing what classes to borrow from where. But in conclusion, by extending MRIO with terms for fMRI acquisition and statistical inference, we provide a comprehensive ontological model of how functional brain imaging data are generated, analyzed, and interpreted. The reuse of Stato and OBCS ensures semantic alignment with broader biomedical ontologies. Newly defined MRIO classes enable formal representation of GLM-based analysis, activation maps, and data-driven methods like dual regression. I mentioned that earlier. I want to highlight again with the GLM-based analysis, that's something that we think is broadly applicable to biomedical imaging as a whole. Like I said, it's not just for MRI or fMRI. But we believe that through this work that we are able to help MRIO better bridge the gap between conceptual ontologies for scientific meaning and pipeline ontologies for data processing, establishing a foundation for the next generation of semantically annotated fMRI datasets. And I'd like to end by thanking the people with Stato, OBCS, and OBI for providing a great framework for us to build off of here. I would also like to thank ICBO for giving me the opportunity to talk today. And here is just a link for all of the work that we have from the MRI ontology, and all of the work that we've done with fMRI. It's available in this GitHub repo. If there's time, I'd be happy to answer any questions you have.